So here are the challenges in machine learning. So the data quality, fitting, ethical concerns, lack of interpretability, and limited data availability. So when we say data quality, ensuring that the quality and reliability of data used for training machine learning models is a critical challenge. Poor quality, alam niyo na, poor quality data can lead to biased models and inaccurate predictions. So for example, in healthcare, incomplete or inconsistent patient records can impact the accuracy of diagnostic models. So dito, kung hindi accurate yung data ng machine learning mo, baka mamali yung diagnosis o yung diagnosis nung machine learning sa sakit mo. So make sure that the data is accurate, reliable, no? Parang sa ganun hindi maging bias or hindi maging challenge yung data quality when it comes to machine learning. Okay? That's data quality. Next one is overfitting. When we say overfitting, no, overfitting occurs when machine learning model is excessively tailored to the training data, performing well on it but failing to generalize to new unseen data. For example, no, in image classification, a model memorizing specific features of training images rather than learning general patterns. So dito is nasosobrahan na yung machine learning mo ng mga features. Depende sa kung ano ba ang dapat na ibigay sa kanyang data. Okay? So, excessively tailored to the training data. So, now over na yung machine learning mo. Okay? Third one is ethical concerns. When we say ethical concerns, no, uh, it encompasses issues such as fairness, transparency, biases, and accountability in algorithmic decision making. For example, no, facial recognition algorithms showing biases against certain demographics leading to discriminatory outcomes. So make sure that the machine learning or the data must be in accordance to what must be implemented, okay, in such a way that it provides transparency and accountability, and it could help in decision making, no? It should not be a bias against certain demographics, okay. That's ethical concerns. The fourth one is lack of interpretability. Machine learning models often operate as black boxes, making it challenging to interpret how they arrive at specific decisions. So, for example, no, difficulty in explaining the decision-making process of a complex deep learning model for credit scoring. So, make sure that yung pagbibigay mo ng instruction is madaling maintindihan ng machine learning mo or ng AI mo, okay? So that's lack of interpretability. Okay. The last one is limited data availability. Machine learning models require substantial amount of data. However, no, make sure that it's not overfitting, or data for effective training and limited data availability can hinder model performance. So, kung kulang ang data sets na meron ka to detect cancer, it won't detect or diagnose a patient if he or she has cancer. Kasi kulang yung basis niya, kulang yung label data test niya to diagnose if it's cancer or not. So make sure that you have a sufficient data about such uh, uh, concerns, no, sa healthcare or sa other industries. So those are the five common challenges in machine learning: data quality, overfitting, ethical concerns, lack of interpretability, and limited data availability. So to finish our discussion, please watch these videos that I have prepared for you.
In a previous video, Martin Draghi, a professor of the IC school at TPFL, told us how machine learning was able to distinguish cats from dogs.
We have 100,000 images for which we really know this is a dog, this is a cat. And for each of them, we have the true answer. That's what we call supervised machine learning.
So basically, supervised machine learning performs very well today. However, what about if we don't know the labels of our data?
So this is a big open question at the moment, which people try to solve. We want to find patterns already in the data when you don't know the true answers. So we try to find at least something meaningful in it. So when you don't know if this image is a dog or a cat, can you still learn something from it? And this is not only about images, this is the same question for text, for business data, for sensor data or time series or audio data or all kinds of data. So can you get useful information from it without knowing the true answer already? And that's what we're trying to do. We try to do unsupervised learning.
Unsupervised machine learning would be a huge breakthrough, since the vast majority of the data available on the internet is not labeled, at least not the way that machine learning researchers would want them to.
I think it might take another 10 years till we can really do this well. The second very big challenge we have is maybe about neural networks. Neural networks work amazingly well in practice nowadays. It's funny because they have always been around for many decades. It's not that the mathematical concept is new, but we have found much more successful applications for them because there is more data. Not so much because they are different now, but because we have found more useful data sets to apply them to.
Artificial neural networks are machine learning algorithms that are inspired by the way the human brain works. These are made of individual virtual neurons that are connected to one another with edges, just like the neurons of our brains are connected by synapses. As we train the artificial neural networks with data, the so-called backpropagation algorithm will adjust the strengths of the links between neurons in the right way. These artificial neural networks have become state-of-the-art for many of the classical machine learning problems like face detection, natural language processing, translations, or driving cars. However, why these artificial neural networks perform so well in practice is a difficult theoretical question. Are they really the final answer to machine learning, or will they be in 5 years a new machine learning paradigm that will render neural networks obsolete? Well, perhaps I would say that nobody really knows, because no one really seems to really understand why neural networks perform so well in the first place.
But what's really lacking is the understanding of why the neural networks work well. So mathematically, they are still the same idea. It's like a regression model. Some input comes in and the network will predict a value. That's the answer it gives. And we train it using gradient descent, like this, trying to make the biggest decrease in the error. But why these neural networks work, or what's the theory, and if this algorithm actually can be understood, is still completely open. We don't understand what these neural networks actually do and why they work well, and if we can make any theoretical statements about it. So it's a big challenge.
Let's move on to the third big challenge that Martin Jaggi mentioned.
So another problem we have in machine learning is that the models we build, they are very specific. They are much too specialized. So we can only do a neural network, we can train it to distinguish cats from dogs. So it's very specific. So if you take this network and want to apply it to a different task, maybe it's not on images, maybe it's another task, or maybe it's just about different things in the image, then this is completely useless. It cannot answer any other questions than it was trained to. And this is a challenge to give these networks ability to do other tasks as well, to transfer at least something they have learned, to also improve a little bit on a different task, because maybe it has been trained on images of something, but now you want to apply it to something else, like a self-driving car, or process a video, or a very different application. The idea, what we'd like to do, is that there are some different levels of understanding in your system. So at the very bottom, there is the raw data, the input. So maybe the pixels if it's an image, or the letters if you're working on a text. And then the system gradually transforms this input into a more meaningful representation. Maybe it tries to combine several letters into a word and tries to represent the meaning of the word. Or maybe if you ask about images, then maybe it tries to group several pixels together and think that, hey, this this is a change of color in the image, this is a little pattern, and then gradually combine these informations into a more high-level representation, which tries to capture the meaning of what is in the input data.
In fact, one reason why deep neural networks seem good at that might be that deep neural networks compute higher and higher levels of abstractions of raw data.
What we'd like to do is to enable transfer learning, to enable the same system or this part of this system to help on a different task. So maybe parts of these networks can also help for the different task, but there's no systematic way yet to enable this or to theoretically understand it. Okay, the last challenge we have is to make these models scale on much larger datasets and larger systems.
It's interesting to compare this with human learning. A human being lives about a few billion seconds, and at each second we collect data through our different senses, through our hands, our noses, our eyes, our ears. We definitely collect a few gigabytes of data at every second, which all add up to exabytes of data all along our lives. Not quite a zettabyte, but close enough. Our computers today are nowhere near such capabilities. They typically only crunch gigabytes of data, perhaps terabytes. As Martin Jaggi said, scaling up this consumption is one of the biggest challenges of machine learning these days. Not only would this require more data, of course, but as well, this will require more sophisticated way to process all of this data, especially given that these days data are distributed throughout a huge network.
So it's surprising, like most of the successful applications in machine learning at the moment, also in deep learning, they are all just trained on one computer, maybe one graphics card in one machine. This actually includes most of the things that Google and Facebook and all these companies have done. So it's a big challenge is to make many computers work together to solve one such problem on maybe larger training data, or to make many devices work together. It could be mobile phones, it could be graphic cards, and to design algorithms which can benefit from the increased computational power, and to find algorithms which enable the devices to work together and to jointly find a solution, to jointly find the model which has the smallest error.
Instead, the algorithm that recognizes faces and suggests tags in Facebook uses neural networks.
We're not going to take the decision away from the doctor, but try to support them, to show them, hey.
Machine learning has revolutionized a lot of industries today. It can help us recognize objects, rank things, even understand what you are seeing. But it is still in its early stage and faces a lot of challenges. Here I will list 3 major challenges in machine learning nowadays from research to industry and tell you what is our current solution to each of them. The first one is lack of training data. Data is at the core of any machine learning project. However, it is usually very hard and expensive to obtain labeled data. How to train a model without a large amount of data is a very hot topic today. Transfer learning is one of the methods to solve this problem. It enables the model to utilize knowledge from previous learned tasks and apply them to the new related one. For example, in the image classification task, very few people will train an entire convolutional neural network from scratch, which usually needs millions of labeled images. Instead, it is common to use the pre-trained models and fine-tuning them on the targeted domain. Self-supervised representation learning is another way to solve the lack of data problems. It opens up a huge opportunities for better utilizing large amount of unlabeled data. Here is a very famous example in language modeling. If there is a sentence, but there are some missing words in it, how can you fill in those missing words? Well, the idea is to predict the missing words by learning from the past and future knowledge. The representation of the language is also learned during this process. Google have used this technique to understand searches better than ever before, which brings one of the biggest leaps forward in the history of search. The second challenge is that there are usually some discrepancies between your training data and production data. Sometimes, the model works well in your prototyping environment but fails to generalize in real-world cases. Let's see a few examples here. The model may work well in one country but failed in another due to geographical differences. The model may work in winter but failed in summer due to seasonal differences. The model may work well on mobile but failed on desktop due to user behavior differences in different platforms. So when you are developing your model, you need to be very careful when you collect your training data to make it as close to your targeted domain as possible and keep updating your model once it is outdated. The last but not the least challenge is about model scalabilities. It is a big issue for a lot of project industry. As a machine learning engineer, you need to make sure that the model can run fast enough and the model size is small enough, which is usually a big challenge for a lot of tasks. One of the possible solutions is to use post-training quantization. It is a conversion technique that can reduce model size. At the same time, it can also improve CPU and hardware accelerator latency, with little degradation in model accuracy. Thanks for watching. Don't forget to ring the notification bell and subscribe.
Hi, I'm Hilary Mason. I'm a computer scientist, and today I've been asked to explain machine learning in 5 levels of increasing complexity. Machine learning gives us the ability to learn things about the world from large amounts of data that we as human beings can't possibly study or appreciate. So machine learning is when we teach computers to learn patterns from looking at examples in data such that they can recognize those patterns and apply them to new things that they haven't seen before. Hi.
Hi,
I'm Hilary. What's your name?
I'm Bryn.
Do you know what machine learning means? Have you heard that before?
No.
So machine learning is a way that we teach computers to learn things about the world by looking at patterns and looking at examples of things. So can I show you an example of how a machine might learn something?
Sure.
So is this a dog or a cat?
It's a dog.
And is this one?
A cat.
And what makes a dog and a cat a cat?
Well, dogs are very playful, I think, more than cats. Cats lick themselves more than dogs, I think.
That's true. Do you think if we look at these pictures, do you think maybe we could say, well, they both have pointy ears, but the dogs have a different kind of body and the cats like to stand up a little different? Do you think that makes sense?
Yeah.
Yeah. What about this one?
A dog. A cat. I think a cat because it's more skinny and also its legs are like really tall and its ears are a little pointy.
This one's a jackal, and it's actually a kind of dog, but you made a good guess. That's what machines do too, they make guesses. Is this a cat or a dog?
None.
None. What is it?
It's humans.
And how did you know that it's not a cat or a dog?
Because cats and dogs, because they walk on their paws and their ears are like right here, not right here, and they don't wear watches.
And so you did something pretty amazing there because we asked the question, is it a cat or a dog? And you said, I disagree with your question, it's a human. So machine learning is when we teach machines to make guesses about what things are based on looking at a lot of different examples. And I build products that use machine learning to learn about the world and make guesses about things in the world. When we try to teach machines to recognize things like cats and dogs, it takes a lot of examples. So we have to show them tens of thousands or even millions of examples before they can get even close to as good at it as you are. Do you have tests in school?
Yeah, I have after every unit, we have a review and then we have a test.
So are those like the practice problems you do before the test?
Well, just like everything that's going to be on the test is on the review.
Which means that in the test, you're not seeing any problems that you don't know how to solve, as long as you did all your practice, right?
Yeah.
So machines work the same way. If you show them a lot of examples and give them practice, they'll learn how to guess. And then when you give them the test, they should be able to do that. So we looked at 8 pictures and you were able to answer really quickly. But what would you do if I gave you 10 million examples? Would you be able to do that so quickly?
No.
So one of the differences between people and machines is that people might be a little better at this, but can't look at 10 million different things. So now that we've been talking about machine learning, is this something you want to learn how to do?
Kind of, because I kind of want to become a spy, and we used to do coding, so I may be kind of good at it.
And machine learning is a great way to use all those math skills, all those coding skills, and would be a super cool tool for a spy.
Hello.
Hi, are you a student, Lucy?
Yes, I just finished 9th grade.
Congratulations.
Thank you. It's very exciting.
Have you ever heard of machine learning before?
I'm going to assume that it means humans being able to teach machines or robots how to learn themselves.
That's right. When we teach machines to learn from data, to build a model from that data or a representation of that, and then to make a prediction. One of the places we often find machine learning in the real world is in things like recommendation systems. So do you have an artist you really like?
Yeah, Melanie Martinez.
So I'm going to look up Melanie Martinez, and it says here, if you like Melanie Martinez, one of the other songs you might like is by Aura. Do you know who that is?
I do not.
So let's listen to a hint of this song.
Okay.
All right. So why do you think Spotify might have recommended that song?
Well, I know that in Melanie Martinez's music, she used a lot of the filtered voice to make it sound very deep and low. And that song had that.
And that's actually a really interesting thing to think about, because that creepy vibe is something that you can perceive and I can perceive, but it's actually really hard to describe to a machine. What do you think might go into that?
Pitch of the music, if it's really low or if it's super high, it could know that. What can the machine understand?
It's a great question. The machine can understand whatever we tell it to understand. So there might be a person thinking about things like the pitch or the pacing or the tone. Or sometimes machines can figure out things about music or images or videos that we don't tell it to discover, but that it can learn from looking at a lot of different examples. Why do you think companies might use machine learning?
Well, I think things like Facebook or Instagram, they probably use it to target ads.
Sometimes the ads you see are really uncanny. And I think that's because they're based on so much data. They know where you live, they know where your device is. It's also important to realize that people in aggregate are actually pretty predictable. Like when we talk to each other, we like to talk about the novel things, like here we're having this conversation. We don't do this every day, but we probably still ate breakfast. We're gonna eat lunch, we're gonna eat dinner. You probably are going to the same home you go to most of the time. And so they're able to take that data that we already give them and make predictions based on that as to what ads they should show us.
So you're saying I give them enough data as it is about what I might be talking about or thinking about that they can read my mind, but just use the data that I've already given them. And it almost seems like they're
That's
watching
right.
us.
To do machine learning, we use something called algorithms. Have you heard of algorithms before?
A set of steps or a process carried out to complete something.
That's right.
So do you think that we've been able to teach machines enough so that they can do things that even we can't do? And on the opposite side of that, do you think there are things that we can do that a machine might never be able to do?
So there are things that machines are really great at that humans are actually not great at. Imagine watching every video posted to TikTok every day. So we just don't have enough time to do that at the rate at which we can actually watch those videos. But a machine can analyze all of them and then make recommendations to us. And then thinking about things that machines are bad at and people are good at. People are really great with only one or two examples of learning something new and incorporating that into our model of the world to make good decisions, whereas machines often need tens of thousands of examples. And that's not even getting into things like good judgment because we care about people, because we can imagine a future that we want to live in that doesn't exist today. And that's something that is still uniquely human. Machines are great at predicting based on what they've seen in the past, but they're not creative. They're not going to invent. They're not going to, really change where we're going to go. That's up to us.
I'm Sunny.
And what are you majoring in?
I study math and computer science.
So in your studies, have you learned about machine learning?
Yeah, I have. So to me, machine learning is essentially exactly what it sounds like. It's trying to teach a machine specifics about something by inputting a lot of data points, and slowly the machine will build up knowledge about it over time. For example, my Gmail program, I assume that there would be a lot of machine learning models happening at once, right?
Absolutely. And that's a great example because you have models that are operating to do things like figure out if a new email is spam or not. So what would you think about if you were looking at an email and trying to decide if it went in one category or another?
I'd probably look at certain keywords, maybe if the recipient and the sender had exchanged emails before and what generally those fell into in the past.
So these are things we would call features. We go through a process where we do feature engineering, where somebody looks at the example and says, okay, these are the things that I think might allow us to statistically tell the difference from something in one category versus another. So for example, perhaps you don't speak Russian, you start getting a lot of email in Russian.
Obviously, the features that you just described are features which a person would have had to think about. Are there features which the machine itself could learn?
This is a great question because it really gets to the difference between some of our different tools in our machine learning tool belt in addressing problems like this. So if we were to use a supervised learning classic classification approach, a person would need to think about those features and creatively come up with them, an approach we call the kitchen sink approach, which is just try everything you can possibly think of and see what works. Unsupervised learning, where we don't have labeled data and we're trying to infer some structure out of the data. You're projecting that data into a space and looking for things like clusters. And there's a bunch of really fun math about how you do that, how you think about distance. And by distance, I mean that if we have two data points in space, how do we decide if they're similar or not?
And how do the algorithms themselves usually differ between unsupervised and supervised learning?
Supervised learning, we have our labels and we're trying to figure out what statistically indicates if something matches one label or another label. Unsupervised learning, we don't necessarily have those labels. That's the thing we're trying to discover. So reinforcement learning is another technique that we use sometimes. You can think about it like a turn in a game, and you can play, millions and millions of trials so that you're able to develop a system that by experimenting with reinforcement learning can eventually learn to play these games pretty successfully. Deep learning, which is essentially using neural networks and very large amounts of data to eventually iterate on a network structure that can make predictions.
With reinforcement learning versus deep learning, it seems to me that reinforcement learning, is it sort of like the kitchen sink approach that you were talking about earlier, where you're just kind of trying everything?
It is, but it also thrives in environments where you have a decision point, a palette of actions to choose from. And it actually comes historically from trying to train a robot to navigate a room. If it bonks into this chair, it can't go forward anymore. And if it falls into that pit, it's not going to succeed. But if it keeps exploring, it'll eventually get to the goal.
Oh, like Roombas.
Yes.
Oh, wow. I didn't realize it was that deep almost. Is there a situation which you'd want to use a deep learning algorithm over a reinforcement learning algorithm?
So typically you would choose deep learning if you have sufficient high quality data, hopefully labeled in a useful way. If you really are happy not to necessarily understand or be able to interpret what your system is doing, or you're willing to invest in another set of work afterwards to understand what the system is doing once you've already trained it. And this also comes down to the fact that some things are actually really easy to solve with linear regression or simple statistical approaches, and some things are impossible.
What would be the outcome if you were to choose the quote-unquote wrong approach?
You build a system that could actually be useless. So years ago, I had a client that was a big telecom company, and they had a data scientist who built a deep learning system to predict customer churn. Actually, it was very accurate, but it wasn't useful because nobody knew why the prediction was what it was. So they could say, you know, Sunny, you're likely to quit next month, but they had no idea what to do about it. And so I think there are a bunch of failure modes.
Would that be an example of like linear regression where the regression is accurate, but you know, for marketing purposes, it's like, if you don't know why I'm quitting the service, then how can we fix this?
Yeah, this is actually a good example of a very real world kind of machine learning problem where the solution to this was to build an interpretable system on top of the accurate prediction. So not to throw it away, but to do a bunch more work to figure out the why.
How can we improve machine learning algorithms?
It's actually fairly new that we're able to solve all of these problems and start to build these products and apply it in businesses and apply it, you know, everywhere. And so we're still developing good practices and what it means to be a professional in machine learning. We're really developing a notion of what good looks like.
I'm in my first year of a PhD in computer science, and I'm studying natural language processing and machine learning.
So would you mind telling me a bit about what you've been working on or interested in lately?
So I've been looking at understanding persuasion in online text and the ways that we might be able to automatically detect the intent behind that persuasion or who it's targeted at and what makes effective persuasive techniques.
So what are some of the techniques you're applying to look at that debate data?
Something I'm interested in exploring is how well it works to use deep learning and sort of automatically extracted features from this text versus using some of the more traditional techniques that we have, things like lexicons or some sort of template matching techniques for extracting features from text. That's a question I'm just interested in general. When do we really need deep learning versus when can we use something that's a little bit more interpretable, something that's been around for a while?
Do you think there are going to be general principles that guide those decisions? Because right now it's generally up to the machine learning engineer to decide what tools they want to apply.
I definitely think there is, but I also sort of see it varying a lot based on the use case, something that kind of works out of the box and maybe works a little bit more automatically might be better. And in other cases, you do sort of kind of, you want a lot of fine-grained control.
So is that where some of that frustration around the lack of controllability and interpretability comes from?
Yeah, if you're building a model that just predicts the next thing based off of everything it's seen from text online, then yeah, you're really going to be replicating whatever that distribution online is.
If you train a model off of language off the internet, it sometimes says uncomfortable things or inappropriate things, and sometimes really biased things. Have you ever run into this yourself? And then how do you think about that problem of potentially even measuring the bias in a model that we've trained?
Yeah, it's a really tricky question. As you said, these models are trained to sort of predict the next sequence of words given a certain sequence of words. So we could start with just sort of prompts like the woman was versus the man was and kind of pull out common words that are sort of more used with one phrase versus the other. So that's sort of a qualitative way of looking at it. It's not ever kind of a guarantee of how the model is going to behave in one particular instance. And I think that's what's really tricky. And that's why I sort of think it's really good for creators of systems to just be honest about this is sort of what we have seen. And so then someone can make their own judgment about, is this going to be too high risk for sort of my particular use case?
I imagine in the last few years, we've seen a lot of changes and improvements in the capabilities of NLP systems. So is there anything in that you're particularly excited about exploring further?
I'm really interested in sort of the creative potential that we've started to see from NLP systems with things like GPT-3 and other really powerful language models. It's really easy to write long grammatical passages, thinking about the way that we can then harness like the human ability to actually give meaning to those words and sort of provide structure, and how we can combine those things with the kind of like generative capabilities of these models now is really interesting.
Yeah, I agree. So hi, Claudia. It's so great to see you.
That's been far too long.
You know, we first met 10, 11 years ago, and machine learning has changed a lot since then.
Tooling that we now have, the capacity and also an elevation of the problem sets that we're dealing with and how to frame the problem. And I'm almost struggling to figure out whether it's a blessing or a curse that it has become as accessible and as democratized and as easy to execute, and you just build another new company from scratch. But so what's been kind of your reflection on that?
Well, you're absolutely right that the attention machine learning gets has grown dramatically. 20 years ago, going to gatherings and telling people what I was working on and seeing the blank face or the like worse, the turn and walk away, like, oh no. The accessibility of the tooling, like we can now do in like 5 lines of code something that would have taken 500 lines of very mathematical, messy, gnarly code even 5 years ago. And that's not an exaggeration. And there are tools that mean that pretty much anyone can pick this up and start playing with it and start to build with it. And that is also really exciting.
In contrast, what I'm struggling with is a friend of mine who asked me to look at some healthcare data for him. And despite the capabilities that we're having in all of the kind of bigger societal problems alongside with data collection, engineering, all the gnarly stuff, that is actually not the machine learning itself. It's the rest of it where certain data isn't available. And to me, it's staggering how difficult it is to get it off the ground and actually use.
And part of the challenge of it is not the mathematics of building models, but the challenge is making sure that the data is sufficiently representative, potentially high quality.
At how transparent do I need to build it for it to be adopted at some point? What types of biases in the data collection and then also in the usage? We now call it the bias, but we're still struggling with the society not really living up to its expectations, and then machine learning bringing it to the forefront.
Right. And so to say that another way, when you're collecting data from the real world and then building machine learning systems that automate decisions based on that data, all of the biases and problems that are already in the real world then can be magnified through that machine learning system. And so it can make many of these problems much worse.
Feeling increasingly challenged that my skill set of being very good at programming has become somewhat secondary, and it's really the bigger picture understanding of who would be using that, how transparent do I need to build it for it to be adopted at some point, what types of biases in the data collection and then also in the usage. I think in certain areas we have societal expectations as to what is fair and what isn't.
And so it's not just the provenance of that data, but it's sort of deeply understanding, why does it look the way it looks? Why was it collected this way? What are the limitations of it? We need to think about that entire process, how we document that process. This is an issue in companies where somebody might create something that even their peers can't recreate.
What have you seen in terms of which industries, where they stand, like who is adopting now, who is ready to utilize it? Where would you maybe wish they didn't even try?
These are great questions. So things like actuarial science, operations research, where they actually are not using machine learning as much as you might think. And then you have other sorts of companies, or on the fintech side, or even the ad tech side of things, where they perhaps are using machine learning to the point of even absurdity.
So I spent about 8 years working in ad tech, and the motivation was really because it was such an amazingly exciting playground to push that technology that used to largely live in academia, really out in the world and see kind of what it can achieve. It has created such a hunger for data that now everything is being collected. I'm curious, when are we going to make a foray into things like agriculture, about smart production of the things we eat? You see and hear these interesting stories, but I feel like we're not ready yet to put that into a economically viable situation.
So when we think about the next 5 to 10 years, the things that are really still holding us back are these uneven applications of resources to problems, because the problems that get attention are the high value ones in terms of how much money you can make, or the things that are fashionable enough that you can publish a paper on it. So what do you think is holding us back?
I fully agree on the steps you pointed out and the processes. I think there is a chicken and egg problem, like your farmer example, that these areas that need to wait for data, the value of the data collection is then also slightly less apparent, and so it gets delayed further, and you see that happening. But what my experience has been, there's unfortunately, I feel, a drifting apart between academia and the uses of AI, but I'm somewhat frustrated with a generation of students who have standard data sets, that they never think about what the model needs to be used for, that they never have to think about how the data was collected. So with all of these challenges ahead of us, how optimistic are you about this world that I deeply believe we can create, and the steps towards it?
I am incredibly optimistic, and perhaps it's a personality flaw, but I can't help but look at the potential of the technology to reduce harm, to give us information, to help us make better decisions, and to think that we would choose to address the big problems ahead of us. I don't think we have a hope of addressing them without figuring out the role that machine learning will play. And to think that we would then choose not to do that is just unthinkable.
Despite the rightfully raised concerns about the challenges ahead, but I think they also make us as a society better. They challenge us to be a lot clearer of what fairness means to all of us. So with all of the setbacks, I think we have exciting years to come. And I am looking forward to a world where a lot more of that is used for the right purposes.
I hope you learned something about machine learning. There has never been a better time to study machine learning, because you're now able to build products that have tremendous potential and impact across any industry or area that you might be excited about.